Okay, here we are. This is part 2. 1.2.0 DC motor types. Two basic types of DC motor connections are in common use, the series motor and the shunt motor. So here's the shunt motor. And when I say the word shunt, I want you to think parallel. Whenever you have a shunt resistor in a meter, that resistor is in parallel with the meter movement. It's shunt. So here's the shunt field winding, and it's in parallel with the armature. Here's the armature of the motor. Here's the shunt field winding. Here's the DC incoming power. So this is a parallel shunt DC motor. Field circuit of a shunt motor is connected across the supply line and is in parallel with the armature. A shunt motor connection is shown in figure 16. When an external load is applied to the shunt motor, it tends to slow down. A slight decrease in speed causes a corresponding decrease in the counter-electromotive force. Because the armature resistance is low, the resulting increases in armature current and torque are relatively large. Therefore, the torque increases until it matches the opposing torque of the load. The speed of the motor then remains constant at the new value as long as the load is constant. So they're very good at speed regulation. If the load on the shunt motor is reduced, the motor tends to speed up. The increase in speed causes a corresponding increase in counter-electromotive force and a relatively large decrease in armature current and torque. The amount of current through the armature of a shunt motor depends largely on the load. The larger the load, the larger the armature current. The smaller the load, the smaller the armature current. All right. I'm going to make that a highlight. The larger the load on a shunt DC motor, the larger the armature current. The main advantage of a shunt wound motor is that its rotational speed is fairly constant, changing only a few revolutions per minute when the amount of load is changed. So its rotational speed is fairly constant. These are things they might ask you about. If a motor is to be started with a large load, it's generally series connected because the shunt DC motors have a low torque at startup. So if you're trying to crush rocks in a rock crusher, you're going to want to use a series wound motor. Warning, never open the shunt field circuit of a DC motor when the motor is operating, especially when unloaded. Open field may cause the motor to rotate at dangerously high speeds. Large DC shunt motors have a field rheostat with a no field resistance or release feature that disconnects the motor from the power source if the field circuit opens. So here are some characteristics of a shunt DC motor. A DC shunt motor has high torque at any rated speed. At startup, DC shunt motor can develop 150% of its normal torque. Speed control. DC motors have excellent speed control. Speed regulation. The speed regulation of a shunt motor drops from 5 to 10% from no load to full load. And here they've graphed. You can see the torque is constant. There's a constant torque with regard to speed. The series DC motor. So here we have the armature, and it's in series with this series field winding. Okay. So the same power, same current runs through the series field winding and the armature back to the power source. So the field coils of a series DC motor are connected in series with the armature. The value of current through the armature in the field is the same. Therefore, if the armature current changes, the field current must also change. As the motor speeds up, the armature current and field current decrease. With a weaker field, the armature speed will continue to increase. The limiting factor of the speed is the load. And then here's a highlight. It says the series motor is used where there's a wide variation in both torque and speed requirements, such as traction equipment, blowers, hoists, cranes, and so forth. It says a DC series motor develops 500% of its full load torque at starting. It's a very high torque starting, the series motor. Speed control. The speed control of a series motor is poorer than that of a shunt motor, because a simultaneous reduction of current occurs in both the armature and the field windings when the load's reduced. Speed regulation, it says the direction of series motors' rotation is changed by reversing either the armature or the field winding current flow. If you change both of them, the motor still rotates in the same direction. So you can't just merely change. If you have a battery and you take that battery and you flip it over, that DC series motor is going to turn in the same direction as it did a minute ago because you reversed both of them. So you have to change the polarity of the series field winding with regard to the armature winding. Compound DC motors, that's when they have both a series and a shunt or parallel winding. The compound DC motor has a normal shunt winding and a series winding on each field pole. So here's the series winding, and here's the shunt winding. They put F for field and S for series. Now here's a long shunt. Remember, the word shunt means parallel. So the shunt winding is in parallel with both the armature and the series winding. That's a long shunt. The short shunt, the field winding or shunt winding, is only parallel to the armature. And then it goes through the series winding. So there's a short shunt and a long shunt. That's the difference. Compound motor avoids some of the limitations of the series wound and shunt wound motors. The shunt field has a constant current, so the motor will not self-destruct like a series motor. The series winding, on the other hand, provides strong torque. So permanent magnet, many quarter to 3 horsepower variable speed motors are available for constant or diminishing torque applications. They use permanent magnets for the field poles instead of shunt or series windings. So in the compound motor, a cumulative compound wound motor develops high torque for sudden increases in load. Speed control, unlike the series motor, the cumulative compound wound motor has definite no load speeds and will not build up self-destructive speeds if the load is removed. Speed regulation, the speed regulation of the cumulative compound wound motor is inferior to that of a shunt motor, but superior to that of a series motor. Okay, so Section 1 review. When studying the operation of electric motors, it's important to remember that magnetic lines of force do not cross. I know, I said I wasn't going to answer it for you. A motor with a field coil is connected in parallel with the rotor winding. When I say shunt, you think parallel. Okay. All right. I'm going to go on to section 2. 2.0.0, AC motor operation. Describe how AC motors operate, identify three-phase induction motors, identify synchronous motors, identify single-phase induction motors. AC motors can be divided into two major types, single-phase and polyphase, or three-phase. The single-phase motor is commonly available in very small fractional horsepower ratings, such as a 1/150th of a horsepower up to about 5 horsepower. They're commonly used to power fans, pumps, appliances, and similar devices. Most single-phase motors are not connected to complicated motor control circuitry. So if you have a sprinkler pump, that's an AC single-phase motor. If you have a swimming pool, that's a single-phase motor. Most anything you have at your house is going to be single-phase because we don't have three-phase at our house. Polyphase motors can drive significantly larger loads and have several advantages over single-phase motors. They do not require a separate winding or other device to start the motor, offer relatively high starting torque, and respond well to speed regulation. There are two classes of polyphase motors, induction and synchronous. The rotor of a synchronous motor revolves at synchronous speed, or the speed of the revolving magnetic field in the stator. None of the induction motors do. We'll talk about that. It's called slip. But the synchronous motor is the one motor that can actually turn at synchronous speed. When you do the math and you figure out, okay, this should be 1800 RPM, that synchronous motor will pretty much be 1800 RPM. How AC motors operate. AC motors consist of two primary parts, the stator, stationary part, and the rotor, the revolving part. The stator is connected to the incoming three-phase AC power. The rotor of an induction motor is not connected to the power supply, while the rotor of a synchronous motor is connected to the external power. Both induction and synchronous motors operate on the principle of rotating magnetic field. So they're describing a three-phase motor, a polyphase motor. And you have a rotating magnetic field in the stator. The stator is connected to the incoming power, and because it is three-phase and those phases are sine waves, you're going to change the north and the south poles through those windings. This section shows how the stator windings can be connected to a three-phase AC input to create a magnetic field that rotates. Another magnetic field in the rotor can be made to chase it by being attracted to and repelled by the stator field. Because the rotor is free to turn, it follows the rotating magnetic field in the stator. So here they're trying to show us, here are your three phases. These are three incoming lines, three phases of power. And as we change those three phases of power, we change where the north pole is. Here's north, north, north. Look, here's your north, north, north. And here's a bold north, and a bold north, and a bold north. So that north pole is rotating around the stator. And then there's a long description of that. I'm not going to read it. Rotor behavior and rotating field. An oversimplification of rotor behavior shows how the magnetic field in the stator influences the rotor. Assume that the simple bar magnet is placed in the center of the stator diagrams shown in figure 22. Also assume that the bar magnet is free to rotate. It's been aligned such that at point 1, its south pole is opposite the large north pole of the stator field. So they're saying that right here, the south pole of this permanent magnet that they've placed inside here, that's not really what it is, but we'll pretend, is going to face the north. And as this north rotates 360 degrees, so too will the south pole of that permanent magnet. It'll rotate if it's allowed to spin freely. As the AC completes the cycle going from point 1 to point 7, the stator field rotates and pulls the bar magnet with it because unlike poles attract and like poles repel. The bar magnet's rotating at the same speed as the revolving flux of the stator. The speed of the revolving flux represents the synchronous speed. At synchronous speed, there's a formula. Here's synchronous speed equals 120 times the frequency of the incoming power divided by the number of poles. So synchronous speed and rotations per minute equals the frequency in the cycles per second times 120. It's a constant derived by multiplying 60 seconds per minute times 2 for one pair of poles, and then dividing by the number of magnetic poles. Induction. Current flowing through a conductor sets up a magnetic field around the length of the conductor. Conversely, a conductor in a magnetic field will produce a current when the magnetic lines of flux cut across the conductor. So this action is called induction because there's no physical connection between the magnetic field and the conductor. So a lot of the rotors in an AC three-phase motor are not connected to a power source. That secondary voltage and current is just induced in the rotor. The torque on the rotor of the induction motor tends to turn the rotor in the same direction as the rotating field. If the motor is not driving a load, it will accelerate to nearly the same speed as rotating field. As the rotor accelerates, the magnitude of the induced voltage in the rotor decreases. This is because the relative motion between the rotating field and the rotor conductors is reduced. So, let's see here, where does it say here? Therefore, there would be no induced voltage, no rotor current, nor no rotor magnetic field and no torque. Basically, what they're describing here is slip. Let's go back to our 3D BB. Oh, come on. There. So what they're saying is, here we've got, all right, this is going to be an oversimplification. I'm sorry, but it's easier to draw simple, so I'm going to draw simple. Here is the stator, the stationary portion of the motor, and here's the foot of the motor, and we're serving it with three-phase power. And basically, because we're doing that, we have a north, and we might have a south and a north and a south and a north. We're just going to deal with one north and one south at the time. I'm not even going to draw the south. I'm just going to draw the north. This north is rotating. It's not really. The coils of wire are stationary, but because they're being served with sine waves, with varying degrees of voltage and varying polarities of voltage, it creates the resemblance of a rotating magnetic field. So this rotating magnetic field is going around and around and around, probably doing 60 revolutions per minute. We might have more than one pair of poles, so we would multiply that. We could say that there was 120 rotations or 180 rotations, depending on how many poles we have. But if I have a stator, if I have a rotor, if I can put a rotor in here, and I can use slip rings, and I can use a DC source, I could feed this through those slip rings to cause a south pole to be here. And when that south pole and that north pole are locked in, well, there we go, let's see here. When that happens, this rotor is going to rotate at synchronous speed. That south pole will hang with that north pole because it has a separate, they call it an exciter. You use an exciter, it's a DC generator, and it generates a DC current through this rotor that causes it to have, I want to use the term permanent, but it's not a permanent magnet. It has a south pole that remains a south pole. Doesn't have a commutator, doesn't change. That south pole is always south. So it follows that north, and it follows it at synchronous speed. That's the only motor that turns at synchronous speed, is the synchronous motor. It's the only one. Reason being, I have to have lines of flux that are cutting this rotor. So let's say that we're not talking about the synchronous motor anymore. We don't have an external power source creating a south and north pole. Now it's just a self-contained rotor. The voltage and current in that rotor are induced because of the rotating magnetic field in the armature, in the stator, in the field windings. So as this north goes by, the lines of flux induce a south pole in this rotor, and it tries to follow the north pole. The north pole keeps going past it. The north pole keeps going past it, and when it flies past, those lines of magnetic flux cut the coils in the rotor, and it creates that south pole, and that south pole tries to catch that north pole. But now, let's say that the south pole does catch the north pole. All right? So now, yeah, that's not exactly working. draw another south over here and another north over here. And then I'm going to grab this one and this one and this one. I'm going to link them all together. That way it's going to turn and stay on my axis. Oh, that's beautiful. If you have a rotor that has to induce voltage and current in the rotor, and the south pole catches the north pole and stays with it, guess what? We're no longer cutting lines of flux. The lines of flux are running parallel, or they're running with this rotating rotor. And the north and the south in this rotor, they collapse. They collapse. So all of a sudden, they start to diminish. They go away. And when that happens, we no longer have that attraction. So what I'm saying is that the rotor can never become synchronous. It can never get to synchronous speed. When it does get to synchronous speed, it's not going to be cutting lines of flux anymore. So the voltage and the current in the rotor are going to decrease. They're going to collapse. When that happens, this rotor is going to slow down. When it slows down, then the north and south poles are going to then cut those lines of flux and reintroduce a voltage and a current in that rotor, and it'll start spinning again. This is called slip. So when I figure the synchronous speed of this motor, and I say, well, the synchronous speed of this motor is 1800 RPM, I figured it out mathematically. Well, this rotor is not going to turn at 1800 RPM. It might turn at 1750. We might get as much as 1770. It's going to be slower than the synchronous speed because we can never catch that rotating magnetic field. I'm not talking about the synchronous motor. Remember, the synchronous motor is fed with DC, and it's the only one that is synchronous. It will be synchronous because the south and the north will join up and it'll continue to spin at that synchronous speed. The ones that are induction motors, the DC induction motor, I'm sorry, not DC, the AC polyphase induction motors, they will not turn at synchronous speed. They will turn at some speed less than. And this 1800 RPM, if you put a load on it, we might only be turning at 1650 RPM. If we have a heavy load on it, it's going to have a considerable amount of slip. All right, I wanted to explain that. So let's go on, because I think they're going to start talking about, oh, look at that. You kidding me? Slip. In an induction motor, the rotor always rotates at a speed less than the synchronous speed. The rotor speed is such that sufficient torque is produced to balance the restraining torque caused by the motor friction and mechanical load. The difference between the synchronous speed and the rotor speed is known as slip. Slip is expressed mathematically as follows. So it's some percentage. In this formula, the quantity is multiplied by 100 to convert it to a percentage. So a 4-pole, 208-volt AC, 2 horsepower, 60 hertz, 3-phase induction motor has a no-load speed of about 1790 RPM and a full load speed of about 1650 RPM. Find the percent slip for each of these cases. All right, well, when we do the 1790, synchronous speed is 1800. They did 120 times the frequency, 60, divided by the number of poles. And what did they say it was? A 4-pole. So they did 120 times 60. Yeah, let me get my calculator out. Let's do it. So they did 120 times 60 divided by 4 poles. And that equals 1800 RPM. That's the synchronous speed of this motor. So here 1800 minus 1790 is 10. 10 divided by 1800 times 100 is 0.556%. Less than 1%. Slip under no load condition. On a full load condition, 1800 minus 1650 divided by 1800 times 100 is 8.33% of slip. Finally, calculate the slip at locked rotor condition. Well, it's 100%. It's locked rotor, it won't go. So very quickly we will burn that motor up if we do not disconnect it from the power. That's what we use in overloads on your motor starter. Your motor starter has an overload block, and it's going to disconnect the power to that motor if there's ever a condition where that motor is not operating at or very close to its rated current. When it's under a lot of drag, the current will go up, and if it's at locked rotor, the current goes way up, and those overloads will open very quickly to disconnect the power of that motor to save the windings of the motor. Okay. The answer of 100% makes sense because the rotor's not rotating at all. Okay. Figure 23 shows how torque relates to speed over the operating range of a motor. Note that speed is proportional to the torque on the left side up to the pull-out torque point. Beyond this point, however, the torque decreases as speed increases. Okay. Slip is the difference between the synchronous speed and the actual speed of the rotor in an induction motor. Slip is necessary to permit the motor action to occur. Under increasing load, the rotor torque increases. Because the percentage of slip is proportional to the torque, the amount of slip will increase. This increase means higher current consumption by the motor due to the greater difference between the rotor and the magnetic field. Motor supply voltages, current, torque, speed, and rotor impedance are closely related. By changing the resistance and reactance of the motor, the characteristics of the motor can be changed. However, for any particular rotor design, the characteristics are fixed. So, starting current. The movement of the three-phase induction motor is energized. The current supplied to the motor rotor stator terminals may be as high as 6 times the motor full load current. This is what we were saying before. This is because at starting, the rotor is at rest. Therefore, the rotating magnetic field of the stator cuts the rotor at the maximum rate, inducing large amounts of EMF in the rotor. This results in proportionally high current at the input terminals of the motor. Because of this high inrush, motor current protection must allow as much as 300% of full load current to allow the motor to start and come up to speed. However, this level of protection can only be allowed for a short time. If the rotor never moves, then the motor needs to be de-energized after a reasonable time has elapsed. Because 100% slip exists at the instant that the motor is energized, the rotor current lags the rotor EMF by a large angle. This means that the maximum current flow occurs in a rotor conductor at the time after the maximum amount of stator flux has passed by. This results in a high starting current at the low power factor, which results in a low value of starting torque. Okay. Oops. Loading torque. If a load is placed on the motor shaft, the rotor will tend to slow down. As it slows down, more flux lines are cut until enough torque is developed to overcome the load placed on the shaft. The motor now runs under the load at a slower speed than before the load was placed on the shaft. This normal range of operation is shown by the lower dashed lines in figure 23. Okay. All right. Overload condition. If the load is increased above full rated load, everything happens as stated before to increase torque up to a certain point. Figure 24 shows typical torque and current curves. Note how the torque climbs as the load increases. Then you get to a point where it will not create any more torque and it starts to fall off drastically. This is the full load speed. This will continue as load increases until the pull-out torque point is reached. Beyond this point, the torque decreases and the motor will quickly stall. A typical situation is when a bench circular saw stalls when cutting thick wood or the wood is fed into the saw too quickly. The motor will slow down as its cutting load increases until it suddenly stalls and hums or growls loudly. The condition will persist until the load is relieved, a fuse blows, or a breaker trips. The motor has simply reached a point where it cannot continue to increase its torque. This is referred to as an overload condition. Any further increase in load will cause a stall. You can very quickly burn up the windings of a motor if this condition is reached, so you need those overloads, that overload block we spoke of earlier. It'll disconnect the power to the motor, saving the motor. So the power factor at no load speed is low because the magnetizing component of the input current is a large part of the total input current of the motor. When the load is on the motor is increased, the in-phase current supplied to the motor increases, but the magnetizing component of the current remains practically the same. This means that the resultant line current is closer to being in phase with the voltage, and the power factor is improved when the motor is loaded compared to with an unloaded motor. So we end up with a better phase angle. This is under load. This is fully loaded. This is no load. So they're saying we have a big theta. We have a poor power factor. Here we have a better power factor because we're coming closer to unity. We're coming to where everything is resistive and we have true power. Reversing rotation. Well, it's very easy to do in a three-phase motor. The direction of rotation of a three-phase induction motor can easily be reversed. The motor will rotate in the opposite direction if the connection of any two leads is reversed. So it's kind of an industry standard that we swap A and C phase. If it's black, red, blue, and you want it to go in the other direction, make it blue, red, black. You swap A and C phase, leave B alone. That's kind of an industry standard. You can swap any two. Here they've swapped B and C. So now instead of going A, B, C, it's going A, C, B. So that's in an opposite rotation. We could swap A and B. We could have BAC, BAC, BAC. Any two. Three-phase induction motors. In a three-phase induction motor, the driving torque is caused by the reaction of a current-carrying conductor in a magnetic field. In induction motors, the rotor currents are supplied by the electromagnetic induction. The stator windings are supplied with three-phase power and produce a rotating magnetic field. So they're going to talk about the squirrel cage motor. The three-phase induction motor has a frame or stationary part, the stator. The stator is made of laminated steel rings with slots on the inside of the circumference. The motor stator windings are the phase windings. So the reason they laminate the frame is because they want to reduce eddy currents. Motor stator windings are the phase windings. Squirrel cage induction motor. The squirrel cage is the rotor design most used for three-phase motors. Three-phase squirrel cage induction motors consist of a stator, a rotor, and two end shields that house the bearings that support the rotor shaft. So here you go. These are the field windings here on the outside, or we call that the stator windings. And then the rotor has a squirrel cage. Basically, we can't see them, but there are bars of aluminum running through this. You can kind of see it. And they're twisted slightly, and that's because of the neutral plane. But yeah, they're twisted slightly, and that helps aiding in that motor running. Here you go. Here's a good drawing. These are bars of aluminum. Copper aluminum bars. And they're separated. But they're shorted at both ends so that you can have current flow through them. Having current flow will allow that magnetic field to be formed. The speed of a three-phase squirrel cage induction motor depends on the frequency of the applied voltage and the number of poles. Oh, that's There you go. There's a highlight. Speed of a three-phase squirrel cage induction motor depends on the frequency and the number of poles. As a result, these motors are used in applications where the speed is either remains constant or can be controlled by other means, such as with a variable frequency drive. Those variable frequency drives are clever. You can change that driving uh, voltage frequency. You can take 60 hertz and you can change it to 0 hertz and it'll be stationary, it'll be stopped, or you can make it 15 hertz or 30 hertz. Some of them you could overclock the motor. If the motor is made to do that, you can go up to 120 hertz and double speed the motor for short periods of time, no longer than about 15 seconds or so. So, squirrel cage induction motors have many favorable attributes. For example, maintenance costs are low because these motors have no brushes or slip rings. They also have a high starting torque, so they're useful in common applications such as overhead doors, large compressors, fans, and printing presses. Wound rotor induction motor. The wound rotor has a winding that's similar to the three-phase stator windings. The rotor windings are usually Y connected, with the three ends of the windings connected to three slip rings mounted on the rotor shaft. Slip rings are shown physically mounted on the end of the rotor shaft. They're used with brushes to form an electromechanical connection to the rotor. So here are your slip rings, and you can supply this with AC wound rotor. Sometimes you'll have a shorting ring that will just allow these to act like a squirrel cage motor. Slip rings are a contact surface mounted on the shaft of a motor or generator to which the rotor windings are connected and against which a brush rides. Brushes are a sliding contact, usually made of carbon, that makes continuous electrical connection to the rotor rotating part of the motor or generator. They're made of carbon because they want them to be soft. They don't want to wear out the slip rings. They don't want to wear out the motor itself. They want those brushes to be worn out. So they will wear over time. Those carbon brushes, they're very soft. When they wear out, you just replace them. They have replacement brushes and they're inexpensive and it's easy to replace them. A schematic representation of a wound rotor motor is shown in figure 31. Wound rotor motor often uses an external Y-connected resistor connected to the rotor through the slip rings. The resistor provides a means of varying the rotor resistance. This helps the motor produce a higher starting torque. So they're not necessarily even connecting this to any source of electricity. They're taking it to a bank of resistors in a Y configuration. And they're variable. You can change the ohmic value of these variable resistors. And in doing so, you can change the torque of the motor. In a wound rotor induction motor, the insertion of resistance in the rotor circuit not only limits the starting surge of current, but also produces a high starting torque and provides a means of adjusting the speed. Speed can be varied by as much as 50 to 75%. The greater the resistance inserted into the rotor circuit, the lower the speed will be below synchronous speed. Let's see here. When the motor operates below full speed, the percentage of slip increases and the motor operates at reduced efficiency and horsepower. If the full resistance of the speed controller is cut into the rotor circuit when the motor is running, the rotor current decreases and the motor slows down. As the rotor speed decreases, motor voltage is induced in the rotor winding and more rotor current is developed to create the necessary torque at the reduced speed. If all the resistance is removed from the rotor circuit, both the current and motor speed will increase. However, the rotor speed will always be less than synchronous. Remember, this is also true of a squirrel cage induction motor. The speed of a wound rotor motor can be controlled manually or automatically with timing relays, contactors, and push-button speed selection. The wound rotor induction motor is used when it's necessary to vary the rotor resistance, to limit starting current, or to vary the motor speed. Because the rotor circuit heat generation is largely external to the rotor windings, the Wound rotor motor is used for applications that require frequent starts without overheating the motor. All right, that's a highlight. Because the rotor circuit heat generation is largely external to the rotor windings, a wound rotor motor is used for applications that require frequent starts without overheating the motor. All right, going green. I'm not going to read going green. Synchronous motors. The synchronous motor is a three-phase motor that operates without slip for no load conditions to full load conditions. These motors are used in precision applications such as manufacturing equipment. The synchronous motor has a revolving field that is energized by a source separate from the stator winding. The rotor is excited by a DC source. There you go, they call it an exciter. The magnetic field set up by the DC on the rotor then locks in with the rotating magnetic field on the stator and causes the rotor to revolve at synchronous speed. By changing the magnitude of the DC excitation, the power factor of the motor can be changed from leading to lagging. Because of the unique ability of synchronous motors to change power factors, they're often used as power factor correctors. They're most often used in applications that require constant speed from no load to full load conditions. Very good. Yeah. All right. You have three stator windings that are 120 degrees apart and a wound rotor that is connected to slip rings where the rotor excitation current is applied. So the stator windings are 120 degrees apart. That's true of all of these polyphase motors. Any three-phase motors we're talking about, the stator windings will be set at 120 electrical degrees apart. So I think we've already explained how this works. This is how the DC motor works once it's started. However, one of the disadvantages of this type of motor is that it cannot be started just by applying AC to the stator. When AC is applied to the stator, the high-speed rotating magnetic field rushes past the rotor poles so quickly that the rotor does not have a chance to get started. The rotor is locked. It's repelled in one direction and then in another direction. In its purest form, the synchronous motor has no starting torque. So when the stator and rotor fields are energized, the poles of the rotating field approach the rotor poles of opposite polarity. The attracting force will tend to turn the rotor in the direction opposite the rotating field. As the rotor starts to move in that direction, the rotating field moves past the rotor poles and tends to pull the rotor in the same direction as the rotating field. The result is a complete lack of starting torque. To allow this type of motor to start, a squirrel cage winding is added to the rotor. This winding is called an amortisseur winding. So that's a highlight, and I guess it's also French. There's an amortisseur winding added to this. Did they show us a picture of it? Where did they show us? They didn't show us the amortisseur winding. Well, that's a shame. All right. So here are your main windings, and then they'll have a small winding in between here. And it's a little added, like they said, basically it's a squirrel cage. It's a squirrel cage rotor. Rotor windings are constructed so that definite north and south poles are created. These poles, when excited by DC, will lock in with the revolving field. The rotor windings are wound about the salient field poles, which are connected in series for opposite polarity. Okay, sometimes this squirrel cage motor will run the entire time. Sometimes the squirrel cage winding will be taken out of the circuit once it comes up to speed. You have shorting rings on the ends of the squirrel cage, and when it gets up to about 80% of synchronous speed, that centrifugal switch will disconnect the shorting rings. So the squirrel cage is no longer, it doesn't have any circulating current, so it has no north or south, so it does not, it doesn't conflict with the rotor of the synchronous motor. All right. Number of field poles must equal the number of stator poles. The rotor field windings are brought out to slip rings mounted on the rotor shaft. Field current is supplied through carbon brushes to the field winding. Again, carbon because they're soft. Okay. And it's laminated. The laminating the core reduces eddy currents. When a synchronous motor is started, current is first applied to the stator windings. Current is induced in the amortisseur winding, which is that squirrel cage winding, and the motor starts as an induction motor. Motor then comes up to near synchronous speed. They say about 5 to 10% of slip. At that point, the field is excited and the motor turning at high speed reaches synchronous speed. The squirrel cage winding will not be generating any current and therefore will not affect the motor's operation. So at synchronous speed, the squirrel cage windings are not cutting any lines of flux. They will not interfere with the workings of that synchronous motor. Amortisseur windings serve an additional purpose when the load changes frequently. The motor speed is not steady. This is because the torque angle oscillates back and forth, trying to settle at its required value. This momentary change in speed creates a current due to induction, and the amortisseur winding develops torque. This momentary torque serves to dampen or stabilize the oscillating torque angle. This is why amortisseur windings are sometimes referred to as damper windings. They're sometimes referred to as damper windings. Okay. All right, I'll start here and start another.